So, welcome to Nonlinear Optics. Still without students, but on YouTube you can follow it, at least. Last time, what did we do last time? We were looking for the first time really at third-order processes, right? And the phenomena that we discovered there are quite interesting. So we said already in the second chapter that we expect a nonlinear index of refraction. And, well, of course we got it. We even were able to calculate N2 just from the susceptibility, from the third order susceptibility. So the nonlinear index of refraction, that has to be added to the ordinary index of refraction. We were quite easily able to calculate that. And then we looked for the consequences, of course. And the first consequence that we analyzed was self-focusing. So it is clear that every usual laser beam, or actually every laser beam, has a certain intensity profile. The intensity is not uniform across the beam necessarily. Usually, or quite often, we have a Gaussian beam, which means that in the middle of the beam, that in the center on the beam axis, the intensity is highest. And this means that if such a even just through air, that, sorry, what is?
I did something wrong. You were down 15 seconds. Sorry.
Okay. Do I need to repeat something? The last sentence. Okay, I repeat the last sentence. So I was explaining that we are that every laser beam has an intensity profile, and if we look at kind of the usual laser beams or a Gaussian laser beam, then this means that the intensity is highest on the beam axis, and this implies that if such a laser beam goes through a piece of glass or just through air, that the ray on the beam axis sees a higher index of refraction and thus has a longer optical path length than the marginal rays. And this is just the same situation that we would have with a lens. And therefore, well, if we have the same situation as with a lens, therefore this beam will converge, will be focused. And well, if it is focused, then the intensity grows higher and higher, and you easily imagine that this leads to kind of a catastrophe, so that the intensity gets infinitely high. Well, that can't be, and sure enough, there are mechanisms in nature that prevent the laser from collapsing to nothing. Most notably, that the material is destroyed, that the intensity gets so high that the material is damaged, which means that you ionize the particles, and this leads to a defocusing effect, and then there can be kind of an equilibrium such that you produce a channel of light. Okay, so qualitatively all of that is clear. We then discussed which kind of intensity is necessary in order to overcome diffraction. So we need a certain critical intensity. Actually, it turned out that it's not an intensity, it's just the power. Very interesting, that it's just a critical power that is necessary to, well, to overcome the effect of the opposing effect, namely divergence due to diffraction. And we calculated that and a few other things. So the upshot is, what we did so far was all in the spatial domain. So we were considering the kind of spatial consequences of the nonlinear index of refraction. Today, we have a different plan. Today, we want to see the consequences of the temporal, in the temporal domain. So if you think about a short pulse, then it's clear that at the beginning of the pulse, the intensity is 0, and therefore there's no impact on the nonlinear, on the refractive index. But as the pulse grows, you have, of course, a different refractive index, which affects the phase of this of the laser beam. Right? So we suddenly have a time-dependent phase. I mentioned that already at the end of the last lecture. A time-dependent temporal phase, which means frequency is the derivative of the phase, which means that you can generate new colors. And in this sense, so if you understand nonlinear optics as the branch of optics where optics gets colorful, so even starting with more or less monochromatic beam, you can create a lot of colors. So this is kind of the hallmark of optics. This is what we encounter now, as opposed to the spatial consequences of the nonlinear index of refraction. So we are concerned with the propagation of pulses today. Well, in order to understand the nonlinear propagation of pulses, it is clever to understand first the propagation of linear pulses through media. But this is, of course, not part of a course on nonlinear optics. This is, well, this is a part of linear optics, more specifically perhaps a part on a course on ultra-fast optics, because generally we would use very short pulses just in order to see more or less immediately some effects. Well, I can't cover the propagation of linear, I can't cover the linear propagation of short pulses through media here for reasons of time. But I wrote a fairly large chapter, chapter 14, on that. And, well, if you didn't do it so far, I encouraged you to study this chapter, well, actually, even before Christmas, but I did it last time again. So if you didn't study it so far, then I urge you to do it as soon as possible. Otherwise, it will be difficult to follow for the rest, actually for this lecture. And you certainly would need to understand this lecture in order to, well, in order to enjoy the rest of the course. Nevertheless, I will give you a very short summary of this chapter 14, just that if you didn't look at it, yeah, so I know students, I've been myself a student, and sometimes the time is not enough or so, and therefore a very short, a very brief upshot of chapter 14. So let's look at a few slides that I have there. Chapter 14, propagation of light pulses. So what we do is that we consider a light pulse that has a Gaussian shape. Well, most of the time you don't have really a Gaussian pulse. But on the other hand, you can say every pulse is at least approximately a Gaussian pulse. Well, more or less every pulse. Yeah? And the point is that a Gaussian pulse shape has nice mathematical properties. In particular, if you take the Fourier transform of a Gaussian pulse, you get, again, a Gaussian pulse. So a Gaussian pulse, which means that the envelope can be written, well, in this typical form. So we have a naught times t squared with a minus sign in the exponential, or as the argument of an exponential function. So this so this index 0 always kind of reminds, or should remind you, that we mean at a certain position, right? We're talking about the propagation of pulses through media, which implies that we not just look at one position, but at, along an axis, say, along the z-axis, as indicated here. Yeah. So now, the interesting part is this phase here, and usually we just would write here omega 0 times t, right? So this is what is probably certainly familiar to you. Well, but actually this phase could be any function. And the most natural thing to do in order to approximate any function would be to include the next term of a power series expansion, right? And also this term here could be dependent on position, on z. Yeah? And again, the 0 indicates here that we are, so to say, at the beginning of our investigation at z equals to 0. Yeah? Okay, so we have a term quadratic in time, just as over there, but here in the second term, we have it with the imaginary unit, right? But nevertheless, we can collect the t squared terms, and we would get this thing here, right? And we can now define this quantity gamma, but this is perhaps not so important. Well, this is the electric field. What we measure, so if you take a photodiode, would be the intensity, provided so the intensity is a function of time, provided that your photodiode is fast enough, which for the pulses that we usually use, femtosecond pulses, is not the case, but then there are other techniques that one could use. Of course, techniques depending on nonlinear optics. Okay, anyway, so if we calculate the intensity, so you see E times the complex conjugate, and we have to decorate it with 2 times the refractive index divided by the impedance of vacuum, which is 377 ohms. Yeah, so you easily calculate from here that I get watts per square meter or so. So if this is ohm and we have volts per meter squared, you easily find that this will give you watts per square centimeter. But anyway, yeah, so that's easy to remember. If we do this calculation here very quickly, then we see that our intensity depends only on this envelope A naught, right? And we have to see what this B is doing. Well, it is, so we can of course calculate the full width half maximum. We see that it depends of course on A naught, right? So the larger the A naught, the shorter the pulse and so on. We can also express it in terms of the standard deviation and so on and so forth. But now, the total phase is this thing here, and as I indicated already, the instantaneous frequency can be calculated by just taking the temporal derivative, and what we see is that we have a time-dependent frequency, right? And a time-dependent frequency, this is called a chirp, because birds consider the music that humans are doing pretty boring, right? So a male bird is trying to excite a female by its singing, but they don't sing like we do with tones. Yeah? So they chirp. They change the frequency of their singing. Right? Because the better they chirp, the more attractive their songs are. Therefore, we call it also chirp. Right? And now, if we have a B naught that's larger than 0, a chirp parameter that's larger than 0, then the frequency goes up and it would sound like hui, right? Whereas in the opposite case, it goes down and it makes xiu. I'm not a good singer, but maybe you can also remember that this sounds happy, right? So the hui and the hiu is a sad chirp, but this is just a joke. Okay, well, I was considering bringing my trombone, but I forgot it. Right, there you can perform a glissando up and down, and this would also be a very slow chirp. Yeah, so the chirp that birds produce is so fast that you won't hear what I try to produce here. Okay. No? So this is how it looks, and you would have guessed that, I guess. Yeah, and then I use many pages on this script in order to explain what happens if you send a beam of light like that through a piece of glass. Right? And what happens is that, that actually the pulse duration, I hate it, that the pulse duration changes. So this blue curve here in this graph, this indicates the dependence of A as a function of Z, and you see that as we propagate through the material, so at the position Z equals 0, say, we have a B naught equal to 0, so this is at least assumed in this graph here, and you see that we get the maximum A naught, which means the minimum of B. And as we continue, the B increases here and the pulse gets longer, right? So you see that well, you see what you kind of expected. It is difficult to produce a short pulse, and therefore it's difficult to keep it short if you do optics with it. So this is basically what this thing here is saying. And the entire mass, this I expand on this in this chapter 14. But the essential thing of this chapter 14, and well, this is also essential, yeah? So no question about that. But the thing that brings us to the next chapter is at the very end of this chapter 14, namely that we try to cast the mass such that the propagation of a short pulse is described by a differential equation, and this differential equation turns out to have the shape of the Schrödinger equation, right? So here it is. So a Schrödinger equation for pulse propagation. I still hope somehow that this thing here works again. Maybe like this. Okay, so perhaps, yeah, at least I get a pointer, so this helps already. Yeah, so what we do in this chapter 14.7, yeah, is a Schrödinger equation for pulse propagation. We start with the usual wave equation, and then we go to the frequency domain and write it in this way, so a Helmholtz equation. And now we substitute for the wave number, we substitute a power series expansion, because we know, of course, that due to dispersion, yeah, so this is not a constant, but it has a frequency dependence, right? So this is, of course, in frequency domain, therefore we did the Fourier transformation. And you see that we get several terms, right? And the interesting one here, the one that is responsible for this pulse dispersion that we observed, so that a short pulse that is sent through a piece of glass, that this pulse in general gets longer. So this is described by this factor here, right? By the second derivative of k with respect to omega. And, well, if we do a few further steps, then we arrive at this differential equation. So now you could say, well, this doesn't look like a Schrödinger equation because there is this term here, right? So if you just have this one here and the last one here, then this really looks like a Schrödinger equation, right? Just replace here the E with a psi, like in quantum mechanics, and it's a wave function. Yeah? And of course, there you would have the temporal derivative here, yeah? But we have the spatial one here, and of course, vice versa here. We have this the second derivative with respect to time in the Schrödinger equation. Yeah? So if we would do quantum mechanics, then we would have here the second derivative with respect to a spatial variable. Yeah? But this here seems to destroy the Schrödinger equation, but actually by a coordinate transformation you can get rid of that. So if you would go into the rest frame or into the frame of the propagating pulse, you can get rid of that, right, of this mixed term. Okay, so this was linear pulse propagation. Now we go to nonlinear pulse propagation, and if linear pulse propagation is described by the Schrödinger equation, by the linear Schrödinger equation, then nonlinear pulse propagation is probably described by the nonlinear Schrödinger equation. Just to be very clear, in quantum mechanics, there is no such thing like a nonlinear Schrödinger equation. Right? So the nonlinear Schrödinger equation is famous in nonlinear optics, but it is entirely infamous in quantum mechanics. There is even a quote by some famous father of quantum mechanics that those who speak of nonlinearities in quantum mechanics, that they are hanged on an apple tree in Bohr's garden in Copenhagen or something like that. Yeah, so not very nice saying, but nevertheless, yeah, just to make the point, this is how they said it. The old fathers of quantum mechanics. Okay, well, now you see what changes and where we start. Yeah, so here we have this k vector, we expanded, but now here we have, well, the refractive index to which we need to add a nonlinear term, and we just, we introduce a few other notations just in order to, to have a little bit more compact notation here, right? So n bar, upper bar, and n2 lower bar, and things like that. Yeah, so trivial stuff, right? And now we write this k, this wave number, we write it in this way, right? And therefore, we get, well, the regular k that we had so far, but we also get a nonlinear part, this delta k. And this delta k is, of course, given by omega naught divided by c times this delta n. So this thing here, this guy over there, right? I already introduced n upper bar and n2 upper bar and n2 lower bar already here. And we use it again here in order to introduce a few more variables. Yeah? Now, whenever you see this G, you know that it has to do with N2, and the details you can always look up. Good. Now, we use this, so this is redundant, so this we don't need. So we do the same steps that we did before, and now we also do this thing that I mentioned before, namely that we go into the reference frame of the pulse, and we also normalize this pulse, right, such that this reference frame is given by this equation here, and in addition we normalize it to, well, the peak amplitude at z equals to 0, right? Okay, and if we do this and introduce a few more quantities, namely if we introduce the dispersion lengths and the nonlinear lengths, then we arrive at this equation, which is the nonlinear Schrödinger equation. Yeah, so it looks like a Schrödinger equation if you have a careful look here. Right, so here we have this typical left-hand side of the Schrödinger equation. Then here, this part with the second derivative. Yeah, so we have it here with a prefactor. Yeah, so usually there would be the mass, basically, right? And here the momentum operator, and then the wave function. And this here is the potential term, right? So here we would have the potential, V of x, and then the wave function, right? And now the interesting thing is, which makes this equation nonlinear, is that the potential term, depends on the wave function, that we have the wave function in the potential, right? The stronger the wave function, or the larger the amplitude of the wave function, the deeper the potential, kind of, right? But let's discuss these prefactors. Yeah, so this dispersion length and this nonlinear length. Remember what I said when we discussed linear pulse propagation. I said that this k double prime, which is the second derivative of k of omega with respect to omega. So you remember that we expanded, here it is, right? We expanded k of omega, and this second term here is responsible for the pulse, so that the pulse disperses, that the pulse length gets broader, and that a chirp is acquired, so that a pulse that had initially no chirp, so it was just a ping, would develop a hui, right? It would develop a chirp. So this thing here is responsible for that. Well, of course, you could ask, what is this thing here responsible for? Well, this just shifts the pulse a little bit in position, but doesn't change its shape or something. And this thing here is particularly interesting, at least for me, because it affects the phase of the pulse, sometimes called the absolute phase or the Carré envelope phase. But this is just a side remark. Well, and you see that this dispersion length depends, of course, on this k double prime, but it also depends on the pulse duration, right? On the sigma. So this is here the standard deviation of the pulse. In other words, you see again, the shorter I make the pulse, the more difficult it will be to keep it short. And this is what you see here. The shorter this pulse, the shorter the nonlinear, the shorter the dispersion length, linear dispersion length. Yeah? Nothing nonlinear here so far. And the bigger this thing here, of course, right? So the bigger this parameter, also the shorter the dispersion length. Yeah, so qualitatively, we immediately agree with this thing here, with this thing being called dispersion length. Well, then we have the nonlinear length, and this nonlinear length gets the larger, gets the smaller, the larger the intensity, and of course it also gets the shorter this length. So which means that on a short length scale something will happen. So the shorter the nonlinear length, as you propagate through the medium, so it's on the scale of the nonlinear length that something nonlinear happens, in the same way that's on the scale of the dispersion length that this dispersion effect, this chirping here, sets in. Okay, well, now we have explained these factors, and well, actually in deriving that I follow point by point, line by line, equation by equation, the same recipe as the one that I used in order to, well, it's no longer here on the slide, in order to derive the Schrödinger equation for linear pulse propagation. So if you still feel a little bit uneasy about a Schrödinger equation for the linear case, then think of your course in quantum mechanics, and one of the first homeworks or examples that will probably be explained was to look at a wave packet, a quantum mechanical wave packet that propagates without any potential or with a constant potential. And what you see is that this wave packet would disperse. Yeah, so just in the same way as here. Right? So the same mass describes the same phenomena, has the same solution, right? Okay, so this is the nonlinear Schrödinger equation. So what you see is that we have two characteristic length scales here. And now I can distinguish four cases quite obviously, right? So either the length of the nonlinear interaction or the interaction of the pulse with the medium. Yeah, so the length of the piece of glass. So this can either be much shorter than the nonlinear length and much shorter than the dispersion length. Guess what happens? Nothing, right? Right? So this is what we expect, that nothing would happen, right? Or hardly anything, that the pulse would come out as it went into the piece of glass, right? Well, then the dispersion length could be shorter than the length of the crystal, which means that we only have linear optics. Yeah, so that nonlinearities don't play a role. And here's the opposite case where only nonlinearities play a role and dispersion, so pulse chirping due to the dispersion doesn't play due to K double prime doesn't play a role. And finally, of course, there's the case where both play a role, right? And this is probably the most complicated and the most interesting. And this is why we postpone it at least to the next lecture and start with the simple things here. But let's quickly look at that before we come to the real interesting stuff, and namely self-phase modulation. How new colors are created. Before I come to that, I just want to discuss this quickly and then go a little bit slower with self-phase modulation. Okay, so I explained that already. Yeah, so if the length of the crystal or of the piece of glass is so short, is much shorter than the nonlinear length and the dispersion length, then yeah, so then then these terms are small, right? Both terms here on the right-hand side is small. The right-hand side is approximately 0, as indicated here, which means that the pulse, u, the pulse as a function of zeta doesn't change, right? So this is just what we expected. Now we can put in a few numbers and just just play a little bit with that. Say we want to do optical communication, and of course for optical communication it would be a good idea if you use pulses that these pulses remain short over the distance of the fiber. So the fiber length, say, is 500 kilometers, and in order to fulfill this, we decide that the dispersion length and the nonlinear length should be 500 kilometers or so, right? And now let's see whether this is possible. So we could use an optical fiber and the telecom wavelengths of 1.55 micrometers. There we would find for a few silica fiber that K double prime is minus 20 picoseconds square per kilometer, or in the units that I like more, minus 20 femtoseconds square per millimeter. So we want the dispersion length to be 500 kilometers. We can't change this thing here because we use that fiber, but we can use a longer pulse. Right, now let's see how long the pulse needs to be in order to fulfill this. And it turns out that it's 100 picoseconds. Yeah, so that would be a pulse that is still rather short, such that you can have a high transmission rate. And so this looks good, right? Now the same thing with the nonlinear length. What would be the condition there? Well, we decide, so we already found that we would take, say, a pulse length of these 100 picoseconds, and now we calculate which intensity can we use. Of course, N2 is given. It's a material property. I didn't know the number exactly, but I know the order of magnitude, 10 to the minus 16 centimeters squared over watts, right? And what turns out is that we need a power smaller than half a milliwatt, which is something reasonable, right? Okay, so this could be done. Okay, other case. Now we have the dispersion length that's much smaller than the length, or approximately the same thing. Yeah, so much smaller is perhaps not necessary. An equal sign, or approximately equal, would be sufficient. So this means that nonlinear term, that the nonlinearities are still negligible, and dispersion dominates. Yeah, so that we are back in chapter 14. And you could calculate for the same example what you could do, right, just to play a little bit. Okay, well, then the third case, and, well, what I say is that this is what I will cover in the next, well, hour or so. And then the final thing here, that's something for the next chapter. Good. Now let's talk about self-phase modulation. About this case where the dispersion length doesn't play much of a role and only the nonlinear length is of importance. So what we want to do is to solve the nonlinear Schrödinger equation for negligible dispersion. And what sounds very sophisticated here is in fact something, well, in the end you will see that strictly speaking we wouldn't need the nonlinear Schrödinger equation for that, but nevertheless I do it with the nonlinear Schrödinger equation in order to get familiar with this beast. Okay, chapter 15, it's actually 15.3 if you look into the script. The solution of the nonlinear Schrödinger equation, NLS, for negligible dispersion. Which means that L is smaller, something like that, yeah, than the dispersion length. Okay, well, this means that we would write the nonlinear Schrödinger equation just with the term for the nonlinear length, right? And skip the last one here, the last term. So for negligible dispersion, LD is so large that the respective term in the nonlinear Schrödinger equation can be dropped. Yeah, and what we then have would be that our Schrödinger equation, yeah, so I have these normalized coordinates, zeta, here, and we just have this term that in quantum mechanics would correspond to the kinetic energy. No, in fact, wrong, to the potential, of course. Yeah. So we have just this thing here. So I gave it the house number 20, this equation. Well, now we need a solution. And the best way to find a solution is to know the solution. In German, and actually international, this is called an Ansatz. Yeah? Ansatz doesn't mean anything but knowing the solution because you're experienced enough or you know the physics well enough. Yeah? So, solution with the Ansatz. And the Ansatz you could have perhaps guessed it because we said already what we expect, namely that the nonlinear index of refraction, well, that the nonlinear part of the index of refraction will change the phase in a time-dependent way, and well, and this we write into our Ansatz. Okay, so what we write is that this kind of wave function is equal to the wave function at position 0. And now we have the exponential, which just has a phase factor. And of course, we need the intensity there. This is what you would expect here. So U squared, this is proportional to the intensity. This is the normalized intensity at the initial position. Yeah? And of course, the ansatz is verified just by substituting it into the differential equation. So in equation 20, so the ansatz also gets a house number. And before substituting it there, I just want to calculate the derivative. So the derivative is, of course, very easy to calculate. Namely, use 0 of tau prime times, now what's in the exponential, namely minus I times theta divided by the nonlinear length times the normalized intensity. And then, of course, the exponential. Right? And now we verify the ansatz. By substituting 21 into 20. Right? And yeah, we find it. Satisfied. Okay, the next thing is that we define a new quantity because, well, what I explained already is that what we have in our ansatz is just the phase. Yeah, so this here is the phase. So look at this imaginary unit. So we have a phase, the nonlinear, and we call it the nonlinear phase, and we give it the usual name of a phase, phi. Right? So define the nonlinear phase shift. That would be the next thing to do. Phase shift phi n for nonlinear, and it's just what's written in this exponential theta divided by ln. Yeah, theta is the propagation distance, yeah, should remind you of z. And then here the normalized intensity. And we are going to play a little bit with this quantity. So this phase shift, this nonlinear phase shift, depends on zeta and on tau prime, and thus it depends on z and t. Right? So let's write that down. This remark. Zeta n depends on z and t. Well, and then you can, of course, write this ansatz or this solution of this simple nonlinear Schrödinger equation. Then you can write it using this nonlinear phase shift. Okay, well, what I did already here was to use variables for the lab frame, and therefore I also want to write the pulse, the electric field in the lab frame. Yeah, so in the lab frame we would have and using non-normalized quantities, yeah, in the lab frame the electric field reads E of Z and T is equal to E naught times E naught and T, yeah, so Z equal to 0, times the exponential, and now all these abbreviations are undone. So I have the imaginary unit z divided by the nonlinear length, and then E of 0 and t divided by E naught squared, and this here also squared. Yeah, and the nonlinear phase shift, for the nonlinear phase shift we would have phi of z of and t is equal to z over the nonlinear length times the intensity at position z equal to 0 divided by the intensity, the peak intensity, so t equal to 0. So that's equation 24 and 25. Of course, you can write equation 25 also in terms of the electric field rather than the intensity. And the nonlinear phase can also be written with the abbreviations that we introduced. So this chi, this variable capital G. Let's do this. So using the definition of G, or Ln, as you wish, 1 over G times the intensity, we could write the nonlinear length as minus z times G times the intensity. So this is the pulse here at position z equal to 0. And then if we use here that G was defined as omega naught divided by C times N2, then we find minus Z times omega 0 times divided by Z times N2, nonlinear index of refraction, times the intensity. Or you could also write minus Z times omega 0 divided by C times delta N. Right, so all the same thing, just using the definitions. Okay, now let's use again a Gaussian pulse and see what happens. And of course, this is entirely trivial. We substitute here a Gaussian pulse, and then we see that the phase changes as, well, a Gaussian pulse, that we have a Gaussian profile for the phase. So for a Gaussian pulse, I of Z, intensity of Z in T equals to the peak intensity times, well, the typical Gauss shape in our notation 2 times A naught times T squared. Then we get that the nonlinear phase is equal to Z over Ln times the exponential of minus 2 times A naught times T squared. That's equation 27. And we can, of course, plot this thing here. I guess I have it somewhere. Yeah, here it is. It looks like this, as you would expect. So the green curve is just the intensity, the Gaussian pulse, and the red curve is what equation 27 prescribes. Okay, now a remark. And this is actually a remark that I could have done and perhaps should have done before. So if you look at this Ansatz 21, where I emphasized that so that the pulse, actually, this is already the remark, that the pulse doesn't change, the pulse amplitude doesn't change, just the phase changes. Right? So this is actually the entire remark. So we see it already at the Ansatz. And you see that, the Schrödinger equation, that it predicts that the pulse will not change as long, so that the pulse, so we can already predict that the pulse will have new colors, but its temporal shape doesn't change. Interesting. So a remark, already the Ansatz 21 implies that the amplitudes u of zeta and tau prime, or of course you can do the same thing for the electric field, don't change. So they are independent. They are independent of Z. Because the argument is purely, of the exponential is purely imaginary. Right? So, and this means the pulse profile, or the pulse shape, does not change. Then, of course, the question is there something that changes at all? Well, I said that the amplitude doesn't change. But, of course, the electric field, so the fast oscillation under the amplitude, that still can change, and it does change. Because we said already that it has to change because the phase of this fast oscillation is affected. We will see, however, we will see, however, that the field E of, say Z and T or so, and you remember when we wanted to emphasize that we mean the full time dependence, we made a tilde on top of the symbol, and in order to emphasize it, I draw it in red here. Perhaps I should even draw it fat. So we will see, however, that the field changes due to a chirp. Changes due to a chirp. Well, this is now a chirp that is not due to dispersion, as it was in chapter 14, but rather it's a chirp that's due to nonlinear interaction. Good. Well, now let's see what happens. Now the chapter, well, what was actually the headline here? Solution of the nonlinear Schrödinger equation for negligible dispersion. This we did, and we introduced the nonlinear phase. Now, the chapter 15.4, self-phase modulation. Self-phase modulation. So we start with a pulse that has no chirp in the beginning, so at z equal to 0. And then in the linear case, we know how the phase develops. It develops like the argument of a wave, so omega 0 times t minus k 0 times z. And in k, there is, of course, the refractive index hidden, and this refractive index we will substitute or will change to the nonlinear refractive index, right? So we start, as usual, with the linear case. So we start with the phase omega naught times t minus k times k0 times z, and replace or add to k0 a nonlinear contribution. Yeah, and then we have the total phase, so not just the linear part, which is omega naught times t minus the k vector in vacuum, yeah, but now times the total refractive index times z. Right? And this can, of course, be written as omega naught times t minus the k, so the wave number in vacuum, times now n plus delta n. I wrote it this way, yeah, times z. Yeah, and this thing here is, of course, omega naught divided by c. Yeah, and we still can recast it in a few other ways. Namely, we can write omega naught times t minus k vacuum times n times z plus, well, just the nonlinear phase that we just introduced. Or we can also introduce an optical path length that is now dependent on the intensity, as we did before, right? So there are many ways to write the same thing. Okay, well, as we already mentioned, we will have a time-dependent frequency. So from 30 follows a time-dependent frequency because the phase is time-dependent. So this omega of t, well, actually of z and t, is equal to the derivative of the total phase. And if we substitute equation 30 or whatever, you find that we get, of course, the derivative of the phase. And because, well, at least if we assume a Gaussian, the derivative can easily be done. but for the time being, we just write it as before, and yeah. And so we have here the derivative of the intensity. Yeah, so this is equation 32. Well, and now we do a Gaussian pulse. So for a Gaussian pulse, we have a defined intensity profile for a Gaussian pulse. I of z and t, well, actually just of t, this case here. Is I naught times an exponential of minus 2 times a naught times tau t squared. So if we do this, then we find that omega of z and t is equal to omega naught plus z over ln. And so the typical thing, you see, if this nonlinear length is short, then the contribution gets large, as before. We have 2 times a naught times t times the exponential of minus 2 times a naught times t squared. Huh? Well, that kind of looks ugly, and therefore it is a good idea to, well, to do a power series expansion of this omega of t. So a power series expansion, in order to see more, an approximation. Power series expansion. Yeah, so we are only interested in the next order. So what we had so far was omega naught, so a constant frequency, and now we have realized that due to this nonlinear interaction, there will be a time-dependent, a complicated time-dependent thing, and because nonlinearities are usually weak, we could say that for a first look, the first order expansion would be sufficient. If it doesn't disappear, right? If it is not 0. Actually it is, so we need to go to this to the second order. So if we do this power series expansion, which is trivial, yeah, so you just need to do the Taylor series expansion, then we find omega naught, as we expect, the leading term, z over the nonlinear length, and well, actually, the first order doesn't disappear. I still have both, yes. Sorry about that. And then here we have the quadratic term. And this is equal to omega naught plus z over the nonlinear length, and then 4 times a naught times t, and then 1 minus a naught times t. Yeah? Good. So we have now a time-dependent frequency, and we could ask ourselves different questions. The first one, and the perhaps easiest one that we could ask is, well, if there are new colors created, but the pulse shape remains the same. And now if you remember what you have read, hopefully, in chapter 14, namely that there is, Yeah? So that if you have no chirp, so if the frequency is not time dependent, then your pulse is shortest. But now I have a given pulse, say at the beginning I have the shortest possible pulse, the bandwidth limited pulse, and I start to create new colors. So I start to make the spectrum broader. But the pulse shape doesn't change, right? So the pulses don't shrink and don't get broader. This automatically means that there must be a chirp. And so it's obvious to ask ourselves, yeah, how big is this chirp? And in order to do that, we just compare this equation 34 with the chirp parameter that we had in chapter 14. So let's write that down. Obviously, there will be new frequencies, which means a broader spectrum. But on the other hand, the pulse profile, the temporal pulse profile, the pulse shape remains the same. So see chapter, well, what was it? 15.3. So this implies some chirp must have been created. Yeah, and in order to compute it, we compare to an expression from chapter 14. In order to compute it, we compare equation 34 to the respective expression from chapter, well, from chapter 14. From chapter 14. Okay. In other words, there we had, in chapter 14, we had 2 times b, chirp parameter, times t, and this should be, at least roughly, equal to equation 34, namely z over nonlinear length 4 times a naught times t times 1 minus 2 a naught times t. Right? And now we drop the quadratic terms and we find immediately the chirp that we have produced. So drop the quadratic term, and then we find that b of z is equal to 2 times a naught. So it depends on the pulse duration. The larger a naught, the shorter the pulse. Let's discuss that. Why this makes sense. So that's equation 35, and now let's discuss it. So we said that the shorter the pulse, the larger a naught. So here we find the shorter the pulse, the larger a naught, the larger the chirp parameter that we produce. This makes sense. The shorter the pulse, the quicker the intensity changes. Yeah, so the shorter the pulse, here it is, the larger the derivative of the intensity. Of course, also the larger the intensity, yeah, so the derivative also scales with the amplitude of I, but it also changes with the pulse duration. Well, and the amplitude of the intensity, this is hidden in the nonlinear length together with N2, right? So, makes perfect sense here. And of course, if I propagate a longer distance, then this interaction takes place a longer time, so to say, and the chirp parameter increases. Okay, so we recast this thing here a little bit, namely by replacing the nonlinear length with the original, with its definition. So using, I think it was 18, at least in the script, the nonlinear length is 1 over g times the intensity, the peak intensity. We can write this chirp parameter also as 2 times A naught times G times I naught times Z, and replacing here G with omega naught divided by Z times N2. So this thing here is omega 0 times Z times N2. We have 2 times A naught times Z times 2 pi over lambda N2 times the intensity, peak intensity. So 36. One consequence that is immediately apparent is that self-phase modulation produces a positive chirp because N2 is always, pretty much always positive. Yeah? Okay, a remark? Self-phase modulation produces a positive chirp. Yeah, so what I called hui, happy chirp, produces a positive chirp because N2 is usually, I don't know a counterexample, positive, but probably there are some. Yeah, and what we also see is that the chirp parameter grows linearly with propagation distance. Good. Now we have answered the chirp thing, right? So how much chirp we produce. The next question, and perhaps it was your original question, is by how much do I broaden the spectrum? So how much do I add to the spectrum, by how much gets the spectrum broader? And this is actually the next subchapter. So 15.5, spectral broadening due to self-phase modulation. So what we have to calculate is the deviation, let's call it delta omega, the deviation delta omega from the original frequency. So delta omega is then defined as omega, so the new frequency minus the original frequency, omega naught. Yeah. We have to calculate the deviation delta omega equals omega, omega minus omega naught. We have to calculate the deviation delta omega from the original frequency omega naught, of course. So this means what we have to calculate is omega equals, well, if you look at the instantaneous frequency, then we just subtract omega naught there, right? And just the remainder stays. So using equation 33 is z over the nonlinear length times 4 times a naught times t times the exponential with this Gauss kind of factor. Right, so that's equation 40. Good. Well, in order to calculate the bandwidth, we would need the time where we have the maximum deviation from the original frequency. Right, so we look for the maxima or minima of delta omega. So the instant, so the time, the instant, and I call it Tm, where delta omega is largest, which means that omega deviates the most, is given, of course, we need to calculate the derivative of that and then find the maximum. Right? So it is given by the derivative of delta omega should be equal to 0. Right? And this is trivial to do. What you find is that Tm is equal to plus minus 1 over the square root of 4 times a naught. And this, by definition, is equal to this sigma. That's the pulse duration, the standard deviation. So the pulse duration defined as the standard deviation of the pulse, the second moment of the pulse, if you want to put it like that. Good. And now we can calculate the maximum deviation by just plugging in this time into this formula for delta omega. So therefore, the maximum deviation this is, well, delta omega maximum, and then I plug that stuff in, right? Z over Ln, just to start with the formula, and then I substitute this here for T. So for Tm, the exponential of minus 2 times a naught divided by 4 times a naught. Right, so this is nice because this is 1 over square root of E. And so we have z over the nonlinear length and then the square root of 4a naught divided by E, the Euler constant, Euler number. Yeah, and then we can actually already give the result here. Yeah, so we have the maximum deviation, and how do I do this here? Yeah, so I can also replace, of course, this A naught with formulas from chapter 14. Yeah, so using the bandwidth, yeah, so the standard deviation of the spectrum given by A naught times 1 plus B naught squared divided by A naught squared. Right? See chapter 14. See equation 14 in chapter 14, so it's equation 16 actually. Yeah. So and an initial chirp of 0 then we find that this delta max is given by the nonlinear so then it's given by the minimum. Do we have this here? Yeah, so it's given by this minimum here. So this is phi nonlinear and the minimum. Yeah, so the strongest phase shift times 2 over the square root of E times the width, the spectral width. Okay, yeah, so you find a few more remarks in the script, but this basically says already what we said. Yeah, so if you look at it mathematically, you would also find, or if you look at these formulas, you would also find that that when the pulse rises, so at the leading flank of the pulse, you will have redshifted new frequencies, so frequencies lower than omega naught, and on the trailing wing you have blue shifted colors, right? And this is nothing else than Hui, right? So then the positive chirp. Okay, now a few final qualitative remarks, and for this I have another slide. Yes, here I have another slide on that. Yeah, so this is what I just presented. So we are creating new colors. We are creating these new colors, of course, coherently. But now it depends what these new colors are doing, right? So we don't create them in as clean a way as well now approximated. We have this Gaussian pulse, so we don't have just this linear part for creating these new colors. Maybe I add here a figure to the script. Yeah, so here you see a figure that depicts yeah. So you see that, so these are so this is delta omega, what is depicted here, and you see that it's not just this part that we considered with our considerations, and we were calculating these maxima, right? And this then gave here the new bandwidth, so to say. But you see that also here happens something. We also create colors here, and of course they can start to interfere. Right? So colors created here and here, they can start to interfere. And now there's something that we didn't consider at all, namely that we could start with a non-zero chirp, a pulse, a chirp pulse. So we could start with, say, a pulse that was chirped just due to material dispersion, either in a positive way or in a negative way. And now we create positive chirps in a nonlinear way. And you immediately guess that the situation where you start with negative chirp and you produce some positive chirp, that this could be particularly interesting. Well, and this is indeed the case. And you see here a few figures that depict this. What is this? So this is what I meant, right? So if you really start, no pointer here, so look at the left panel here. If we start with an initial chirp parameter of equal to 0, well, we see some interferences, right? It's particularly strong, as you might have expected, if we start with a positive chirp and we add more positive chirp, that things get, well, kind of irregular, whereas when you have the situation where both can kind of cancel, you get a fairly, well, kind of regular structure. But one would need to do numerical calculations. I think it's not possible to compute these things here analytically, but numerically it is actually not a big deal. So this concludes chapter 15. I'm perfectly in time. I'm happy about that. And next time we'll start with, well, with the most interesting case in some sense, namely the case where we have nonlinear and dispersion effects at the same time. Perhaps I should add here to this chapter on self-phase modulation that we hardly use the nonlinear Schrödinger equation. Right? We could have done all of that without the Schrödinger equation pretty much. So we used it kind of, well, because we had it, we used it in the beginning and we found, we did this ansatz where the pulse shape didn't change. But actually we would not have needed a Schrödinger equation for that. And then we continued quickly with this nonlinear phase that we could have guessed otherwise also, because the nonlinear phase just contains what the nonlinear phase should contain. We have a time-dependent refractive index, that's all. And so we could have calculated the chirp parameter and also the spectral broadening without referring to the nonlinear Schrödinger equation. This will change in the next lecture when we will discuss an intriguing interplay of dispersion and of nonlinear effects. Solitons will be the result. See you next Monday for an excursion into solitons. Thank you.